Okay, so we were going through permutations and permutation groups. So far we have seen that every permutation can be represented as a product of disjoint cycles, and further that every cycle itself can be represented as a product of transpositions, that is cycles of length 2 or 2 cycles. So that means any permutation can be written as a product of 2 cycles, and this allows us to then classify permutations into even and odd permutations. So that's where we are going to start off today with this definition. A permutation theta in Sn is said to be an even permutation if it can be expressed as a product of an even number of transpositions. Okay, so for example, you can consider this thing. By this definition, this product itself, it is also a permutation, and it is a product of 2 transpositions, so it's an even permutation. Now, the above definition insists that theta have one representation, at least one representation as a product of an even number of transpositions. If that is the case, then this definition is saying that such a permutation theta will be called an even permutation. But at the same time, simultaneously, it may be the case that theta also has another representation as a product of transpositions, where an odd number of transpositions are there. It may happen, we don't know yet. Perhaps theta also has a representation as a product of an odd number of transpositions. Fine, it may have. Then you may ask, so what is the big deal? The thing is that this definition insists that theta have at least one representation as a product of transpositions where there are an even number of transpositions, and that's just it. we don't have to even bother about this fact, which may or may not be true, that simultaneously theta is also expressible as a product of an odd number of transpositions. However, we will show that that cannot happen. Okay. So the author says we first want to show that this cannot happen. Oh, and by the way, let us also note this fact that according to this definition, a permutation is not an even permutation if in any expression of the permutation as a product of transpositions you always have an odd number of transpositions. That's what this definition is also saying. Okay, because it's a definition, and evenness only means, at least one such representation is there, then we call such a permutation an even permutation. So that means if such a representation cannot be found, then it is not an even permutation. Now Herstein is saying that we will prove this, but at the same time he himself is not happy with the way he is going to prove it, or at least tell us how to proceed to prove it. So in his words, frankly, we are not happy with the proof we give of this fact. We give of this fact for it introduces a polynomial which seems extraneous to the matter at hand. So a polynomial will now be introduced, which is a polynomial in several variables. Using that, somehow it will be proved that once a permutation is expressible as a product of an even number of transpositions, then that's just it. You may be able to express the same permutation as a product of some transpositions in a different manner, but there also the number of transpositions will be even. The actual number of transpositions may change, however the parity of that number will not change. If it is even, then it will stay even. So we consider this following polynomial in n variables. Consider the following polynomial in n variables. We know this notation. We have already seen these things in ring theory. So the polynomial is defined as a product of linear polynomials, that is degree. We cannot say degree 1 because these are multivariate polynomials, but all the variables are in their first power. That's what we are saying. I mean, all the factors that we are going to use here, they are having first powers of all the variables. And the factors look like this: xi minus xj, where of course I and j, each one of them varies from 1 through n, but there is a restriction that I is strictly less than j. Maintaining this restriction, all these factors will appear, whatever can appear in this product, and the resulting polynomial we are denoting by this p. And there is one example. But before we go to that example, we want to say how we are going to use this polynomial to show that theta is, that thing that we are claiming, that the evenness will not be affected. So if theta belongs to Sn, you can understand that if we are considering our permutation from the symmetric group of degree n, then we have to consider this n variable polynomial. So for example, if you have S3 here, then you will consider a polynomial of 3 variables, this polynomial where n is 3. So if theta is in Sn, let theta act on P as follows. So theta will send the polynomial P to this thing, that is, okay, well, so P, that notation itself has not been used here. However, the author again writes this, what the polynomial actually is here also. I think in order to emphasize the, to show what we are going to do to this polynomial, theta sends this polynomial to this polynomial x I theta minus x j theta, and this condition of course remains the same. So actually what we are writing here, strictly speaking, is that we are defining a sort of function whose input is in fact the permutation theta and the output is this polynomial. Although it looks like theta is doing something to this polynomial, it is changing this polynomial to another polynomial. Fine, but it can also be thought of as a function whose input is theta and output is this polynomial. So that means if theta changes, naturally this thing will change. And one more thing, do not get confused with this notation I theta. Keep in mind, in this text we are writing functions to the right of the argument. So this I theta actually means, in your more familiar notation, theta of I. Okay, that's just it. Now we are going to illustrate this with one example. And the example that Herstein has taken is this. Before the example he writes something else. Should I write it now or should I write it afterwards? Let me write it now itself. It is clear that theta sends the polynomial, whatever theta is, to either the polynomial itself or its negative. Now, although Herstein writes it somewhat casually, it is not so clear to me, at least. It may at once be clear to you because you may have really understood what is going on here if we replace these subscripts by their theta images, but it is immediately not clear to me. It will become clear once we state something else, something more specific. Now, before going to that, we now have this example. For instance, if our theta is this permutation 1, 3, 4, this 3 cycle multiplied by the 2 cycle in S5, then theta sends our polynomial. So now our polynomial is what? It has, because the permutation is coming from S5, so now the polynomial will have 5 variables. So we are writing in detail so that there is no room for confusion. Now, according to the definition of this polynomial, you can see what we have done here, how we have defined it. So we will do what? First we will fix I and then we will vary j according to this restriction, and then we will change I and repeat that thing. So let us first take I equal to 1. So that means j can then be 2, also j can be 3, j can be 4, then j can be 5. Okay, that's just it. These are all the values j can take. Then we take I equal to 2 and repeat this procedure. 2, 3, 2, 4, 2, 5, then 3, 3, 4, 3, 5, and there will be one more factor, 4 x4 minus x5. You cannot take I equal to 5 because there is no j greater than I then. No such symbol is available. So we have run out of symbols. So this is the polynomial, and this will be sent by this particular theta to, now we are going to write the other polynomial. To sends this to, Okay, so what will theta actually do to these subscripts? 1 will be changed to 3. Okay, so 1 will be changed to 3. So to avoid confusion and to stop ourselves from committing any mistakes, let us first of all write these factors where we have x1. So x1 now will be x3, and how many of them do we have? 1, 2, 3, 4. x3, then let's just save these spaces. Okay, now 2 is sent to 5 by theta, so this will be x5. 3 is sent to 4, x4. 4 is sent to 1, x1. Okay, then 5 goes to 2, so x2. Then we tackle these next 3. So x2 becomes x5, x5 minus x5 minus x5 minus. So 1, 2, 3, 4, then this one. So 3 goes to 4, that means x4. 4 goes to 1, x1, and 5 goes to 2, x2. Next, these 3. This 3 means this 2 first of all, so 3 becomes 4. Four becomes 1, and I'm getting confused. 4 becomes 1, then 5 becomes 2. Okay, and 4 becomes 1, 5 becomes 2. So this polynomial has been turned into this polynomial. Now you can see, you can note here that we are going to continue this calculation. Okay, you can note that in some of the factors the variables are actually the way they should be. That is, the first variable suffix is less than the second variable suffix. I is less than j. For example, this factor. So this factor, we just keep the factor like that. Here also x3 minus x4, 3 is less than 4, so we keep it as it is. Here, however, 3 is greater than 1. So we change this. Okay, so we are going to write x3 minus x5 times x3 minus x4 times minus x1 minus x3. This one also needs to be changed. Minus x2 minus x3. Then this one also needs to be changed. x4 minus x5. We may end up taking a lot of space, but that's okay. The understanding is what we want. Minus x1 minus x5. Okay, then again minus x2 minus x5. 1, 2, 3, 4, or okay, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So next this one. x1 minus x4 then x2 minus the how many sign changes we are going through times this one of course we need not change times x1 minus x2. Now first of all note that all the factors that we had in the original polynomial actually are also present here. Let us see one by one. X1 minus x2, so this is okay. X1 minus x3, or we can just simply, because we know the pattern here, we can simply look here. X1 minus x2, x1 minus x3, then x1 minus x4, x1 minus x5, then x2 minus x3, x2 minus x4, x2 minus x5, then x3 minus x4, x3 minus x5, and finally x4 minus x5. And you can see that the number of factors also is of course the same, because we have just simply changed some factors, that's all. The number of factors does not change. So that means that this final expression actually is either the original polynomial p or it's negative. That much now it has become clear. That remark that the author immediately wrote, it is clear that theta sends p to plus or minus p. But which one is it actually going to be? How many minuses do we have? 1, 2, 3, 4, 5, 6, 7. So that means this is minus our polynomial. It's the negative of the polynomial. And what does Herstein write? Which can be verified to be minus of p. Yes, and we have in fact verified that here just now. Okay, so p has been sent to minus p. Now can we look at the original permutation theta and see whether it is even or not? You see, 1 3 this is a 3 cycle, so a 3 cycle is we cannot yet say those things, no? So it will come afterwards. Okay, how can I immediately say evenness and oddness right now? Because we haven't defined odd cycles, odd permutations yet. So the next thing we are going to, this is where things will now become clear. So what I was just now going to say, that is premature. We cannot yet say those things. Now having seen that any theta actually sends, although of course we have not actually seen that any theta sends p to either p or minus p, we have just seen one example, but still this raises the question, how are you going to decide which one p, whether p will be turned into p or minus p? How will you decide that? Can you decide that without going through this calculation and just looking at theta? Yes, you can. And in fact, a special case of this entire thing is this next thing. If in particular theta is a transposition, that means it's a 2 cycle, then theta, theta sends, this is again our general polynomial, to minus of itself. Okay, and this is something we will verify while we solve the exercises. So the author writes verify, and everything rests on this fact. So what we see here, if we just take it to be true for now, that if our theta is a 2 cycle, is a transposition, then that polynomial will be sent to its negative. So that means what? That just simply means that if you express theta as a product of transpositions, say such an expression is there, such an expression of course will be there, that's what we saw in the previous video also, then instead of applying theta at once to the polynomial p, you can apply theta in stages by say first applying this transposition to p, and then applying the next one, and then the next one. Like that you end up applying all the transpositions to p and its image, the image of that, and so on. So then what you see is that actually, because you are going through this transpositions, and each time you apply a transposition you get the negative, so you will get alternately positive, negative, positive, negative. So it ultimately does not matter exactly how many transpositions theta has in its representation like this. For example, what I am trying to say here is that the actual number does not matter, but rather its parity matters. If there are, say, exactly 4 transpositions, then first of all you apply one of them, p gets turned into minus p, then again that minus p gets turned into p, then p gets turned into minus p, then minus p gets turned into p. So that means ultimately we end up with p. And if in place of these 4 transpositions, another expression of theta as a product of transpositions, say, has 8 transpositions, then this fact will not change. That, I mean, if these transpositions are again then applied on p, you will still end up with p, because the first 4 will take you to p, and then the next 4 will again take you to p, through that sequence, minus p, p, minus p, p. So whether 4 or 8, that does not matter, but the fact that these numbers are even, that matters. Okay, and if this number is not even, then you can of course see that you will end up with minus p. In particular, if this number is exactly 1, then you have minus p, and that is what we have written here. Okay, so now if you believe this fact, which we will anyway prove in the exercises, then it becomes clear that once you express theta as a product of an even number of transpositions, then that same theta cannot have an expression as a product of an odd number of transpositions, because then that same theta will once when you apply that representation which has an even number of transpositions to p, that will give you p. Whereas if you apply that other expression where we have an odd number of transpositions, that will give you minus p. That cannot be, okay, because theta is a single permutation. So that's why the author writes, thus if a Permutation theory. Instead of writing theta, Herstein has decided to write capital Pi. I don't know why, but it's just a permutation, that's it. Can be represented as a product of an even number of transpositions in one representation. One of the representations of this capital Pi, which is a permutation, has an even number of transpositions involved. Then it will keep P fixed. It will not change P to minus P. In one representation, then it fixes P. It leaves P fixed. Same meaning. Thus, if a permutation Pi can be represented as a product of an even number of transpositions in one representation, then it leaves P fixed. So that any representation of Pi as a product of transpositions now must have an even number of transpositions. Any representation of Pi as a product of transpositions must have an even number of transpositions, because you have an odd number of transpositions and P is not fixed. P gets changed to minus P, and this is why this establishes the fact that the above definition, with which we started this video today, of an even permutation is a significant one. It's not just an arbitrary definition, but it has some, that classification is not meaningless. So what this little discussion also reveals is that if a permutation has an expression as a product of transpositions where an odd number of transpositions is involved, then it will of course change P to minus P. So that oddness will persist. In any expression of that permutation as a product of transpositions, the actual number of transpositions may vary, but all those numbers will be odd numbers, because p has to change to minus p when you apply theta to weight, is a significant one. We call a permutation odd if it is not even, and these are precisely those permutations which are expressible as a product of an odd number of transpositions. And because of this even odd thing, the following facts are now clear. Number one, the product of two even permutations is an even permutation again. Why is it clear? That is because say theta is an even permutation and say tau is also an even permutation, another one possibly. Then in any expression of theta as a product of transpositions, you have an even number of transpositions. Say, just for the sake of simplicity and specificity, let us take 4. So theta is a product of 4 transpositions. Tau is also even, so it also has in any expression, it's also a product of an even number of transpositions. So say in one such expression it has 10 transpositions involved. Then what is theta tau? You can of course express theta tau in a very direct manner or in a very straightforward manner as a product of transpositions by just simply writing these two products side by side. So that will give you a product of an expression of theta tau as a product of transpositions, where 4 plus 10 equal to 14 transpositions will be there. So that number 14 is also even, which is the sum of these two even numbers. So by our original definition, theta tau is also an even permutation. So that's why we have this one. And now you can understand similarly, in a very straightforward manner, we have these other two things. The product of an even and an odd permutation is an odd permutation. As is the product of an odd permutation and an even permutation. That also needs to be separately mentioned because product of permutations is not commutative. And that same argument here amounts to oddness of the product, because an even number plus an odd number is an odd number. as is the product of an odd permutation and an even one. And I need ink first. And number 3, of course, the product of two odd permutations is an even permutation, sorry. Because odd plus odd is even. The rule for combining even and odd permutations is like that of combining even and odd numbers. We know now why. Even and odd numbers. Numbers in this context, of course, means integers. But this is no coincidence, for the latter is used to have these 1, 2 and 3, because that's how we obtain these properties 1, 2 and 3. Even number plus even number is even, even plus odd is odd, and odd plus odd is even. Okay, now let an be the subset of the symmetric group of degree n Sn consisting of all the even permutations. So we have collected the even permutations in Sn, and we are calling that collection, that set, an, a suffix n. Note that an is non-empty, since the identity element in Sn belongs to An. Let's just see for a moment why, how exactly. According to our definition, then E has to be an even permutation. According to our definition of An, is E an even permutation? All we need to show is that there are, E can be expressed as a product of an even number of transpositions, which of course is the case, because you can, for example, write E like this. Since every 2 cycle is an inverse of itself, so this will give you E. And in fact, this is something you can also directly verify. 1 goes to 2, then 2 goes back to 1. 2 goes to 1, 1 goes back to 2. So this actually does not change anything. And if there are other symbols involved, they do not appear at all, so they are fixed. So everything is fixed, that means this is the identity. Anyway, so An now becomes a non-empty subset of Sn. What more is true about An? An is also closed under the product in Sn, and that is just part 1. Part 1 of these properties. By 1, An is also closed. And keep in mind that this group Sn is a finite group. It has n factorial order. That many elements it has. No matter how large n factorial is, it is finite. So this is a finite group in which we have found a non-empty subset that is closed under the binary operation of the group. So it will be a subgroup, because when we are dealing with finite groups, and in fact even in an infinite group, if you have a finite subset which is non-empty and closed, then that becomes a subgroup. So now our An becomes a subgroup of Sn. Hence An is a subgroup of Sn. And is this where An is going to be named? No, it will be given its name afterwards. Now the next thing we want to show is that this An is actually not just any subgroup of Sn, but a normal subgroup of Sn. Keep one thing in mind, we still don't know the order of An. Okay, that thing we still don't know. Now we show that An is a normal subgroup of Sn, and in showing this normality, in fact we will do something which will reveal the fact that An is a normal subgroup of Sn, and also additionally it will tell us the exact order of An. Consider the set W consisting of the real numbers -1 and 1. Clearly, W is a group under multiplication of real numbers which is a fact which probably you already know, or it's extremely easy to verify. Now, define the function psi. You can call it psi or you can call it f also. The function name does not matter. The author is using psi. Sn of Sn into W by this rule. Theta psi is equal to Herstein writes S here now, so let me use S. S psi is defined to be equal to 1 if S is even, and it is defined to be equal to -1 if S is odd. I am going to digress a little bit, and we are coming back to it, okay, but before that something else came to my mind. Now itself I should make it clear, later on I may forget. Okay, so even permutations we have defined, and we have shown that once you express a permutation as a product of an even number of, we have not actually shown, but it is a fact that once you express a permutation as an even number of transpositions, that evenness does not change. The actual expression may change, but the transpositions themselves may change, and the number of transpositions involved, that may also change, but the evenness of those numbers does not change. Now, the way we seem to have gone through the argument is that we defined a polynomial, and then we somehow applied theta on this polynomial to give us something else, which turns out to be either plus p or minus p. And then what we were saying is that, so the expression of this theta as a product of transpositions, that ultimately gives us p or minus p, right? So once you get p, you should again get p. The fact that this, the entire argument rests on that fact, that once you get p using one expression of theta as a product of transpositions, then any other expression of theta as a product of transpositions should also give you p. But why? That is because this is a function. That means it's a well-defined function. So when we show these things in the exercises that actually if this theta is a transposition, then we get minus p. While showing those things, we will also prove that this association which links this polynomial p to its image under theta in that particular way produces a well-defined function. So that for a given input, for a given theta, there is a unique output, and that is why the expression of theta as a product of transpositions does not matter. Okay, so we have to prove that. Unless we prove that this is a well-defined function, then actually we have not done anything. Okay, so we will do those things, but right now let us come back to our discussion. Okay, so we have defined a function from one group to another group, and we see this. Now once we define any such function like this, you already know by now that it has to be first of all shown to be well defined. Now that requires two things. First thing is that if you take anything from Sn, from the domain, and that anything is your S. Now keep in mind that S is coming from Sn means S is a permutation on n symbols, and the definition of the function tells us that it is either 1 or minus 1. So these images of course belong to W, so that part there is no problem with that. But the second part is that for a chosen S, these images should be, whatever the image is, it should be unique. If our input is an even permutation, then the image is defined to be 1. If it is odd, it's defined to be minus 1. Okay. Now, according to our definition of even and odd permutations, every permutation is either even or of course not even, and not even means odd by definition. So that we get of course exactly either 1 or minus 1, and we of course get at least one of these two. So that means psi in fact is a well defined function. But something else is also true. Instead of going through those details that I said right now, we just simply write clearly this is well defined. Also, by those properties 1, 2 and 3, psi is a homomorphism. Exactly how? You see, say you take two permutations S1 and S2. You take their product and you apply psi on it. Okay, we just see the calculation roughly. Now there are 4 cases. S1 and S2 are both even. If S1 and S2 are both even, then their product is also even. In fact, that is property 1. So S1 S2 is even, so by the definition of psi this is 1. But 1 is also 1 times 1, and S1 is even means 1 is S1 psi, S2 is even, so 1 is also S2 psi. So you can see that the product has been respected by psi. What happens when S1 is say even and S2 is odd? Then their product is odd by property 2. So S1 S2 is odd, so this is minus 1 by this definition. But minus 1 is 1 times minus 1, and in place of 1 you can write S1 psi because S1 is even. In place of minus 1 you can write S2 psi because now S2 is odd. And there will be a similar one when S1 is odd and S2 is even. And finally, if both S1 and S2 are odd, then their product is an even permutation, and that is property 3. So this psi image will be 1. But 1 can be written as minus 1 times minus 1, and each, those minus 1s are, one of them can be replaced with S1 psi and the other one can be replaced with S2 psi because S1 and S2 individually are odd, and that is why psi is a homomorphism. Okay. Something else is also true. Also, psi is clearly onto. Now here there is a very minute point which which one may ignore, okay, very easily. The point is that if n is equal to 1, that means if you are in the symmetric group S1, then what is S1? S1 actually has nothing but the identity permutation. So this is the trivial group consisting of a single element. If you have this S1 here, then this part is not present, because the only small s that you have in this group is the identity, which is even. Okay, so in this single case, if n is 1, psi will not be onto. But that single case is of course a degenerate case and something which is ignored. Okay, it's just one case. For all other cases, psi will clearly be onto. But how exactly? If you, for example, decide to ask yourself, okay, let me see how exactly is psi onto, then you have to show that both these images actually occur as images of some input under psi. But that is easy. If n is greater than 1, then the elements in Sn are permutations of what set? Of this set of n symbols, right? Now, because n is greater than 1, in the smallest possible case also you have at least 2. So that means you can consider this permutation, which is just a transposition. And by the definition of this evenness and oddness, this is an odd permutation because it already has an expression as a product of permutation, as a product of transpositions where exactly one transposition is there. That number 1 is odd. So it will not change. Now, no matter how you express this in a maybe different manner, the oddness will not go. You cannot make it vanish. You cannot turn that oddness into evenness. That's what we saw. So this is an odd permutation, and that is why -1 is the psi image of this odd permutation, and this odd permutation is in Sn. It's an element in Sn, and 1 of course is the image of this identity permutation, which is even. So if n is greater than 1, then it is onto. And in fact, let us just mention this, although it is something very insignificant, but nevertheless, if we don't mention it, then technically we will be wrong. Onto, we are considering n to be greater than 1. Okay, so now we have something. Now we have a homomorphism psi of the group Sn onto the group W. What is the kernel of this homomorphism? Looking at the group W, you can clearly see that because it's a group under multiplication of real numbers, so the identity element is 1. And the kernel of psi by its very definition is the inverse image of 1 under psi. That is, it is the set of those elements in Sn which all of them get mapped onto this identity element 1. Furthermore, the kernel of psi is precisely this subgroup An by the very definition of psi, being the kernel of a homomorphism an is normal in Sn. Okay, because every kernel is a normal subgroup. And in fact, if we define this function psi after defining an itself, that would have also proved, this argument that an is a normal subgroup of Sn. So actually there is no need to separately show that an is a subgroup of Sn. But the fact that an is a subgroup of Sn comes so directly from property 1 that it's nice to just simply observe it that way also. An is normal in Sn by theorem of, I need to mention the number. Luckily I have the number here, 271. This quotient group is isomorphic to our little group W. Hence, because we are dealing with finite groups, so they will have the same order. The order of this is 2, and the order of this quotient group, we already know how to calculate the order. This is order of the original group divided by order of the normal subgroup. This one, the numerator, we know to be n factorial thus from these equations we ultimately get the fact that the order of an is this, half of the order of the original symmetric group Sn, and that is why an is a normal subgroup of index 2 in Sn. And this is our final conclusion. And before we write the conclusion, now we are going to of course name that an to be the alternating group. So the author writes an is called the alternating group of degree n. And we summarize all these things in this next result. So you can now probably understand why the author was saying that we are not happy with that proof of the fact that evenness does not go away, because suddenly out of nowhere we introduced a polynomial, that too of several variables, and used it in a very strange way to get the fact. There are other proofs also of this fact. But Herstein has chosen to use the polynomial. And this lemma is just simply this: Sn has a normal subgroup of index 2. Index 2 an, or like this, the alternating group an of degree n, which consists of all the even permutations of Sn. And this is where this section ends. After this we have the exercises which we will start solving in the next group theory video. In the next section we will come across one equivalence relation called conjugacy. Recall that while proving Lagrange's theorem, we came across one equivalence relation like this: A congruent to B modulo H, which its definition is just where H is a subgroup of a given group G, is this. Using the fact that this is an equivalence relation, we ultimately did some things, we went through some arguments, and the Lagrange's theorem dropped out as a consequence. Now in the next section we will see again one equivalence relation which will lead us towards something called class equation, and at the end of that next section we will come back to this Sn, and there we will see that the equivalence classes of this new equivalence relation conjugacy, which are called conjugate classes, they can be determined for these symmetric groups in a very nice manner. We will see these things. Okay, so that is all for tonight. If you want to make some remarks on these things, so you can write in the comment section below, or you can mail me at my address. The link will be there in the description. And this actually I was supposed to film it yesterday, no? So yes, but yesterday I had some work. But this next Friday, fields we can do afterwards. Let's just again go to vector spaces this coming Friday. So that's just it. I am signing off for tonight. So see you on Friday with vector spaces. Until then, this is me, Lucifer, from the mathematical room. Have a nice night.